and we will continue with our next speaker, Alexey Gunya from Lebedev Physical Institute in Moscow, who will be speaking about acceleration of high-energy protons in active galactic nuclei. Please, you have 25 minutes.
Okay, dear colleagues. My name is Gunya Alexey. I'm an aspirant from Lebedev Physical Institute. Unfortunately, I confused the time between Moscow and Europe, so I have only 15 minutes. But anyway, I'm glad to be here, and especially I would like to thank Martin for the invitation to the RAGtime. Today, I would like to talk about another view on the problem of the cosmic ray acceleration mechanisms in the AGN. The questions of the origin of ultra-high energy cosmic rays has been open for more than half a century, and the list of the sources and mechanisms responsible for the emergence of ultra-high energy cosmic rays is very extensive, and it assumed that the mechanisms of stationary acceleration by an electric field in the vicinity of the black hole is the most energetic and efficient of all the existing ones. And in the AGN, the high energy proton acceleration process begins in the magnetosphere, the inner area in magnetosphere, and ends in the relativistic jets with different regimes, different scenarios. The proton is interesting because it's almost 90% of cosmic rays, and because it's experienced lower synchrotron losses during acceleration, especially, for example, incomparable to an electron. The proton energies have limiting values for non-active nuclei and active nuclei and intergalactic medium. And ultra-high energy protons can exceed the energy threshold where the dissipation of relict photons has a significant effect. And the main sources of cosmic rays, as you know, are the suns, the pulsars, supernova, and gamma radio bursts, and of course, AGNs. And the different acceleration mechanism can be implemented in the cosmic rays sources, such like electromagnetic stationary acceleration, MHD, supernova shockwave, and very popular magnetic field lines reconnection. And the main instruments for registering high energy cosmic rays, for example, the Cherenkov-Hess, orbital Fermi. But for our purposes, for real energy estimations with quite precise localization of the proton acceleration in the AGN can give us the neutrino detectors, like IceCube, for example. In our case, it's neutrino events in the blazars due to high energy protons collisions. And of course, the process responsible for the transfer of rotational energy of the black hole to matter and eventually to the jet formation is one of the most successful mechanisms for explaining this is the Blandford-Znaik process. And in the turbulent process of plasma accretion, the plasma magnetic field lines are moved to the black hole, and the rotation of the black hole also causes the rotation of the magnetic field lines. And stored NMOs 10 to 62 erg, almost energy is transferred through the rotation of magnetic field lines, which leads to the appearance of a polar electric field. The black hole transferred to magnetic field and NMOs rotation energy very long time and in non-stop, and that's the general reason why that acceleration process called stationary. And the Blandford-Znaik, it's like dynamo machine concept. And eventually, the acceleration proton in the magnetosphere shifted towards the light cylinder by centrifugal force. That's like a similar beat on the wire, classical task, a beat on the wire. And the light cylinder is an imaginary surface where the linear component of the particle velocity tends to the speed of light. And of course, this whole process is possible for rotating black hole at angular velocity, which directly affects to the angular velocity of the magnetic field lines. As a result, the total energy, limiting energy extracted from the black hole is equivalent to the black hole potential. And the acceleration of the proton begins in the innermost accretion disk region during turbulent accretion. Next, a proton receives the bulk of its energy in the region of the magnetosphere. Part of the protons after acceleration can leave a giant vicinity. However, most of all continue to accelerate in the jet. And after gaining maximum energy, ultra high for cosmic rays, proton leave the jet. The main plasma of the jet, part of the plasma collides with the cloud and forms a reverse current. There's and this closing the circuit. And this is the approximately energy which proton achieve in this energy in the for magnetosphere, and this Lorentz factor is for all AGN with jet, magnetosphere with jet, all cycle. The magnetosphere has the structure of an electromagnetic field, which in particular form the trajectory of particles accelerated toward the light cylinder. And the magnetosphere is made up of toroidal and poloidal magnetic field, and the toroidal field becomes much larger than poloidal one in the region of the light cylinder for systems with energy and with jet. Non-active nuclei have insignificant toroidal field. The rotation of the poloidal magnetic field produces a polar electric field. And the topology of magnetic field lines of the magnetosphere has a helix-like structure. And the magnetic field structure considered as a split monopole, means divergence-free and uniform. The acceleration of proton in the magnetosphere is described by a system of differential equations of motions in the spherical coordinate system. And the equations contain the numerical parameters of the magnetic field and magnetization with analogous to the Mitchell criterion for magnetosphere of neutron stars. Since the motion of the proton is also described by inertial forces, it's especially it's more important is the centrifugal force. The acceleration is described by a fuel kinetic approach. This contain a Lorentz force and inertial forces, centrifugal and the Coriolis. And inside of light cylinder, the centrifugal force is more important because particle shifted to the light cylinder surface, and there particle achieve the bulk of energy incomparable to the base of start plate of acceleration. And yes, there's magnetic field parameters. It's relations between toroidal and poloidal magnetic fields, and the magnetization parameter. It's also described as Hillis criterion, according to which particle in an accelerator means magnetosphere in this case, with a magnetic field gains minimal energy before particle leave the accelerated. Before particle leave accelerator. And the proton starts oscillations near the black hole and shifted to the light cylinder inner edge due to centrifugal force. The toroidal momentum actually practically not differ from the behavior of Lorentz factor. As you can see, the poloidal components much smaller than toroidal momentum, and that is the centrifugal acceleration. That's a general idea. And from the solution for the magnetosphere, it can be seen that the proton gains the bulk of energy near the light cylinder surface, and the thickness of this area is the same for non-active and active nucleus. So this solution is similar for non-active and active galactic nuclei. And for active nuclei and non-active nuclei, we have different dependencies for reaching the maximum energy. For AGN, in the beginning, the alpha parameter, which relation between toroidal and poloidal magnetic field, is much smaller because the poloidal field, equipartition magnetic field, is more significant. But due to acceleration, in-process acceleration of particle, when particle move to the light cylinder in the AGN with jet, their toroidal fields becomes much bigger than poloidal, and there the alpha became much more than in the beginning. So the 2/3 these exponents, you can see the angle this dependence. This dependence 2/3 is it's common exponents, energy exponents for any AGN nucleus, and the non-AGNs it's only square from the magnetization, means square from magnetization. So the energy in the AGN proton achieve much more energy than in non-AGN, and the distribution functions also show that there are much fewer high energy protons for AGN, which actually explain their rarity. And for magnetosphere, depending on the nucleus activity, the proton can eventually take on different energy values. As well as our galaxy doesn't have jet, the high energy protons with PV, it's theoretical maximum PV energies accelerated in the vicinity of the central black hole can achieve that energy due to electromagnetic stationary accelerations, which also correspond fresh data obtained at HESS. And for high energy estimating and their source localization in the AGN case, we need, of course, neutrino analysis. As well as in the magnetosphere, the magnetic field of the jet also has a helix structure consisting of longitudinal magnetic field and toroidal magnetic field. In this case, we have similar uniform electromagnetic field, and there the electric field in the jet has a radial component. And our calculations show that longitudinal jet magnetic field have little more complex flux inheritance from radial poloidal in the magnetosphere magnetic field to the longitudinal magnetic field in the jet. The main reasons are field and plasma disturbances and perturbation in the base of jet. The increasing of the initial energy achieved before in the magnetosphere by proton in the jet starts from the intersection area of parabolic and conical profiles in the jet. And the acceleration in the jet is described by the same equations, but in a cylindrical coordinate system. The equations contain the numerical parameters of the magnetic field and electric field values. So, in the physical reality, the potentials of the jet and sorry, wrong slide. Yes. Yes, with further acceleration of a proton in a relativistic jet, depending on the parameters of the electric and magnetic fields, there are three different scenarios possible, three regimes. The first scenario the electric field amplitude is large and proton is accelerated in untrapped regime, gaining maximum energy and going beyond the jet. In the second scenario, parameters of electric and magnetic field approach each other values, which leads to the trapped regime, where the proton oscillates between axis and boundary along the jet axis. In that regime, the proton achieves max energy and close to the jet edge, but loses again to the initial value close to the jet axis. And the third scenario is non-accelerated regime. Here, the proton has only initial energy with insignificant oscillations along the jet axis. The physical reality, the potentials of the jet and the black hole also determines the acceleration regime. If the voltage potential black hole is a little greater than voltage of the jet, then the proton is accelerated in the untrapped regime to the maximum energy. Otherwise, the proton will be accelerated in the trapped regime. And we believe that regime, the trapped regime, characterized for the strong collimation jet with strong current. For example, second type Fanaro-Freile or something like that. And here you can see the table which contain values of the jet and the magnetosphere energies potential for different very famous sources. And we also systematic parameter for microquasar because it's a similar object and they're also the same acceleration process, so it can be very interesting. And you can say it's great, of course, but how it all connect with reality. And as I say in introduction, there only one method at that moment now for the energy estimation and localization of high energy proton acceleration process is the neutrino analysis. And in that year, our colleagues analyzed data sets contains about 400,000 neutrino events and create a correlation model with Blazar's map in the jet center in the subparsec scale. The incoming neutrino energy achieved about 100 TeV to 1 PeV, which nearly coincides with initial energy of the accelerated protons in the top of light cylinder, like here. Yes, this is initial energy on the top of light cylinder, and I think it's great. We have different acceleration scenarios, and first the proton is pre-accelerated in the vicinity of the black hole, and next proton achieve bulk of energy near the light cylinder, but the proton doesn't achieve a maximum energy in the magnetosphere because, as we propose, of the special relation between toroidal and poloidal magnetic field in the magnetosphere. It's very old puzzle behavior and relations between magnetic field in the magnetosphere, and finally, proton achieve maximum energy in the relativistic jet, and only in the case untrapped regime. And a little bonus, the energy generated by black hole for the case non-active nucleus also only partially achieved in the magnetosphere by proton. And in the next work, we will consider the possibility of achieving the maximum energy by proton, perhaps in Fermi bubble. And more details about high energy proton acceleration you can find in these articles. The calculations for the projects were also carried out on the Amazon servers. Or if you have some questions, I like to ask and get your answer. So, dziękuję.
Thank you very much, Alexey, for a very nice talk. So now we have time for questions, please.
I believe David has question.
Okay, David, just unmute yourself and.
Sorry, this question was for the previous talk, so not for this talk. Sorry.
Okay, are there any questions for this talk?
Okay.
maybe I could ask then, because the equations of motion which you have shown, if I understood correctly, they are in flat space-time, right?
Yes, in flat.
And how is it connected? How is it connected with the mass of a black hole, which you later shown in the tables?
Okay. The mass of a black hole with magnetic field and equipartition magnetic field and a mass black hole in general deriving energy which particle can be achieved due to acceleration. If you the mass of black hole, first of all, it's oh, just a moment, the demonstration. Yes, the mass of black hole is it's a power which particle power of which particle particle can can get from the black hole due to rotation. The mass and the magnetic field in combine. It's yes, it's power for a particle acceleration. It's general parameters. It's your question, or?
Yeah, more or less, yes, yes. Thank you very much. So, are there any other questions? So, I don't see any rising hands. So, if there are no any questions, so let's thank Alexey again. Thank you very much.
Thank you.